All right, everyone, 6, 1, 2, 3, and 4. I'm going to run through these real quick for you. If you guys have any questions, go ahead and stop me. I can explore that concept a little bit more, try to explain it in a different way. Otherwise, I'm just going to run through these notes and then hopefully even start to do a few examples with you. And then we can practice on our own, individually with our groups, together in our breakout rooms. Okay, so the first thing, we got to do a little bit of defining of what we're dealing with here in this very first section in this new chapter, this new unit. And those are called exponential functions. And you guys may have heard a lot of that lately with COVID. And I know it's been a year. I know we're all in our rooms or offices or garages right now, trying to learn instead of being in the classroom because of it. But you guys may have heard of them saying flattening the curve. That's been a concept that's been thrown around, terminology that's gone on a lot. It all has to do with this exponential growth. So for example, if I had COVID, right, and then I passed it to 2 of my friends, well, then it just doubled. And if they passed it to 2 of their friends, right, and then they passed it to 2 of their friends, you can see that it's doubling each time, right? So when we deal with these types of things, then you guys remember when we had, and let me use a different number. What did I have there? 3 added together, how many times? Well, obviously you can see 4. So instead of just doing 3 plus 3 plus 3 plus 3, we said there's a shortcut. We can just do 3 times 4. And we just took the plus sign and turned it a little bit and called it timesing, for lack of a better term, because that's what we had. We had the 3 4 times. Okay, but then what happened when we had 3 times 3 a bunch of times? Well, we had to come up with something else. And that's where we created exponents, because it meant something completely different. Repetitive addition, we multiplied. Repetitive multiplication, we put that weird little exponent, we called it, which is where we get the name exponential functions. Okay, so I don't know if you guys even understand technology much. You can see my background, a bunch of zeros and ones, but a lot of you have smartphones and you take a lot of pictures, videos, things like that, mostly of yourselves, but that's a whole nother story. Okay, just kidding. Not selfies, they're called ussies because we do them together, right? But when we do those pictures, there needs to be storage. And you guys know it's based off of gigabytes, right? Well, all of the storage, it used to be called megabytes. That was huge. That was a lot of storage. But then technology kept improving, so they needed to have more runtime and all those other things that come along with it. That's actually how they measure gigabytes. It's all by 2 to the 10th, 2 to the 20th, 2 to the 30th. And then they bump up from gigabytes to terabytes, and so on and so forth. Those are all exponentially driven as well. And so we're going to talk about a couple of things called growth and decay, which is all going to depend on, Megan Trainor taught us this, it's all about that base. Okay? The base is the thing that matters, whatever has the exponent on it. And they use b to let you know that we're talking about the base. Now you guys know the leading coefficient is going to tell us how the end behavior is, right? If it's positive, then it's going to increase. If it's negative, then it's going to decrease. And because we're shooting up and out, or out and then up, you can imagine there's going to be things called asymptotes involved again. Okay? Not necessarily vertical, but this time we're going to have horizontal only. Okay? So this is the generic form of these. And how are we going to know if it's growing or not? Well, if it was 1, then it wouldn't change at all, because 1 squared, 1 cubed, 1 to the 100th are all 1. So that's the one that we're going to gauge the growth versus decay on. And if it's bigger than 1, then obviously it's going to double, it's going to triple, it's going to quadruple, it's going to grow. But if it's less than 1, now notice it's still greater than 0. meaning we cannot have negative bases. Okay? No negative bases. Because when negatives are involved, and I raise those to the power of different numbers, this would be a -2. This would be a +4. This would be a -8. You see our outputs get really crazy. And we don't want to jump from a negative to a positive to a negative. Remember, we prefer things that are smooth curves. Okay, we need things to be functions and pass that vertical line test. And if we had negative values for our base, graphs are ugly. There's no generic way. All right, so just a few little pieces of notes there, and then we're just going to start with a quick little graph. So if you want to grab a photo of that or whatever, it's totally up to you. But that is what we're going to be focusing on and talking about, is all of those different options there. Okay? So again, we're not going to have a base that's 1, and we're not going to have a base that's negative. And if our A is positive, we know it's increasing. A is negative, it's going to decrease. And we'll talk about the domain and range of these things with this quick little function right here. So if you don't know what a graph looks like, what can we always do to find it? We can plot points, right? Just pick some values. Draw what we call a t-chart because it looks like a T. And are we going to choose x's and find y's, or are we going to choose y's and find x's? Well, notice they're telling us what y is equal to. So we're going to choose x values and work it out to see what comes out. Input versus output. Remember, domain and range are all the x values, the inputs. Range will be all the y values, the outputs. Follow the alphabet. D comes before R for domain and range. X comes before Y. So the domain, all my inputs, X values. Range, all my Y values, outputs. So what are some good ones to plug in for X?
0.
That's usually our favorite. Now careful, we're plugging in exponents. Remember, these are called exponential functions because the X is in the exponent. And what does anything to the 0 power give us?
1.
Very good, Kev. 1. So there's 1 point. 0, 1 right there. Anybody know what it looks like yet? Probably need some more points then, right? So I'm going to choose like a 1 and a 2, maybe even some negative values. And we'll talk about negative exponents real quick again as well. But what's 2 to the first power going to give me? 2. That's easy. Careful. What's 2 to the second power going to give me? What's 2 squared?
4.
Good. And even if I put in 3, careful, quick, what's 2 to the third?
8.
Ah, good. I try to rush you because a lot of people put 6. Remember, it's 2 to the third power. It's not 2 times 3. Okay? So that would be an 8 there. Now, what about -1, -2, and -3? What happens when we put a negative up in our exponent? Do you guys remember reviewing those in Unit 1?
It's a fraction.
Yeah, very good. 2 to the -1. Remember, negative exponents? We got to take that, and to make it positive, happy again, we got to move it across. Now, I can always say there's a 1 up there, so I now have 1 over 2, which is just 1/2. So notice when we plugged in 1, we got 2 over 1. But when we plugged in -1, we get 1 over 2. What do we call that, my friends? When we take something and flip it? What's the fancy math term?
The reciprocal?
Very good, Anthony. Reciprocal. So what's going to happen when I put a -2 in, since we already did with the 2 up there? What's the only change? We'll get the reciprocal of 4 when we plugged in the 2 and squared it. How about 2 to the -3? What is that going to give me?
1/8.
Very good. And notice I had this. That's the one we started with. And then when I plugged in 1, 2, and 3 for x, I got out 2, 4, and 8. How are my y values changing every time I went up by 1 in my x? Notice it doubled every time. And remember what we said happens when we just have repetitive multiplication? It's 2 to a power. Now, what power depends on how many times we're going to end up doing that thing, right? If it's 3 times, then notice I would have had it 3 times. Okay, so if I plot these points, the 1, 2, and I'm going to use a different color just so that you guys can see. 1, 2 would be over 1 up 2. 2, 4 over 2 up 4. And notice it is not a line. It has to therefore have some bend, some curve to it. And if I put in 3, I'm going to be all the way up here at 8. If I put in 4, I'd be all the way up there to 16. Now, what about the other side, though? Because I can definitely connect this and kind of see the pattern there. What about the left side?
It's going to approach 0.
Ah, very good. I love the word, the terminology that you used there, Kevin. That's something that we just talked about in the previous unit, wasn't it?
Yeah.
Approaching. That's when we said x approaches or y approaches. We use that symbol, that arrow notation. And you said approaches 0 because what would happen if I put in a 10 or a negative 10?
Just gets smaller.
Yeah, I get 1 over 2 to the 10th. And what do we say happens when we put a really, 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 really big number down here? It approaches what number?
0.
Yeah, it gets smaller and smaller and smaller, but will it ever reach 0?
Nope.
That means we have to show them that it's approaching 0 and never actually crosses through. Because if I tried to graph these, I would go left 1 only up a half. Left 2, half of that. Left 3, half of that. And so if I start drawing this, it kind of looks like it's just going to keep doing this, right? But will I actually ever reach negative values? No. Even if I stuck in negative 100, I'd get this, which is getting close to 0, but it's still something. It's not 0. It's definitely not negative. Okay? So be careful with negative exponents and be careful with your drawing. I'm going to do this, and to show them that that does not actually hit the x-axis, I'm going to draw, what do we call this?
Horizontal asymptote.
Ah, very good. I like that you added in the horizontal, Kevin. That is called a horizontal asymptote, which is a line. And therefore, you should be able to give me the equation of that line. What's true about every point on this line here? Are all the x's the same value?
All the y's.
Good. No, it runs left and right. So that means it's all the y values. And what are all the y values equal to?
0.
Good. Now, of course, can we move that up and down? Can we move it left and right? Yeah, we'll get there. Okay, that's second section. So our horizontal asymptote for this one would be y equals 0. And would you call this an increasing or decreasing graph? How do we read?
Left to right.
And what is it doing as my x's get bigger and bigger and bigger? What are my y's doing?
Increasing.
That's right. So we would call this an increasing exponential graph. And is it a function? Yep. They told us that right at the beginning. We don't even have to test and do the vertical line. We can see, yeah, it only hits one place for every one of these x values. But they told us that at the beginning. Okay? What if I wanted to make it decreasing? What would I have to change that to?
A -2?
Now careful. Can we have negative bases?
Ooh.
Mm.
No.
Yeah, remember we said increasing decreasing. Growth
Oh,
or decay. So what
so
could
I
I
see.
do?
Make it less than 1.
Yeah, so I could actually throw the negative up there, which would in turn flip this to be 1/2. 2 to the negative x, right? A negative exponent, we said, would just flip this. And if I had 1/2, guess what would happen to all of these positives and negatives?
Did it all get smaller?
They would just flip-flop,
Oh,
right? Because if I had 1/2 to the first, I'd get 1/2. To the second, 1/4. To the third, 1/8. And if I had 1/2 to the -1, now I would have 2. -2, 4. -3, 8. But notice this would still be there because 1/2 to the 0 is still 1. So this is the key point. I'm going to call it our vertex again, that starting point, that key point that we're going to deal with over and over and over. It's actually called our Y-intercept as well. But if I wanted to change the values of this thing and rewrite it as y equals 1/2 x, 1/3 x, 1/5 x, any fraction between 0 and 1, then it would now do this. And I would still have that horizontal asymptote, but now on the right side. And now it would be called a decreasing instead of an increasing exponential. Okay? I use that joke about Meghan Trainor and it being all about that base so that you guys remember that's what matters, is the base. Okay? If it's bigger than 1, it's going to grow. If it's a fraction between 0 and 1, it's going to decay. You guys all good with that? See what they mean by flattening the curve? They're talking about asymptotes. But if they said that, everybody'd be like, what? Except you guys. You guys know what they're talking about. Okay? So if we want to talk about the domain and range of these things, notice anything for the x's, whether it's an increasing or decreasing, we can plug in any x value and we will get out some y value. But will we get every y value?
nope.
Will we include 0 in it?
No.
Notice the parenthesis there. A few of you missed a problem on the test because you put a parenthesis and not a bracket. You didn't know the difference. Maybe you didn't know it mattered. Okay? Make sure that you either include it or exclude it. Okay? Open versus closed. See that? Okay? Our end notations. Okay? As x goes to positive infinity, if it's increasing, our y goes to infinity. As x goes to negative infinity, our y goes to 0. Okay, all the things that we already talked about last unit. Okay, the nice thing is, if you learn that, we're just going to keep building off of it with these new functions. Okay, and just make sure when you are asked for asymptotes, you give the equation. Okay, some of you are just putting points or numbers. That's not an asymptote. Okay, it's a line, a borderline. Right, and whether it's y equals 0, x equals 0, make sure that you understand which. Okay, all right. So what we will be doing with these things are many, right? And I'll get to some of the basics, but if they give you just 2 data points and they tell you it's an exponential function, then you can use the x and the y to find the a and the b, right? But you may have to set up 2 equations and set the 2 y values equal to each other so that you can just find the b first or then the a. So things that you guys are going to have to get used to and work through. Just trying to give you a few notes of it. Okay. Given a graph, how can you figure it out? Well, see how it goes from one x to the next for the y values. Is it doubling each time? Then you know it's 2. Okay. Is it getting smaller Is it taking half, 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 half each time? That's how you can find your base based off of graphs. Okay, things like that. And then just knowing the form and making sure that you use any y-intercepts points like that, and knowing whether that's positive or if the a is going to be negative for decreasing. Okay, we'll do some of those as we work throughout this week. One of the most important things in all of this is, what do we all care about? Money. Okay, and compound interest, actually Einstein, you guys may have heard of that guy before. Albert Einstein said that this is the single most important discovery in all of mathematics, is compound interest. And that's pretty bold statement, but because he's who he is, you can tell that it really does matter. Okay, so we'll get into a little bit of this, not too much, but this is something that you guys definitely should know in order to move forward in life. Because this formula right here is how you find compound interest. And it depends on the rate that you are given. If you guys have a checking or savings account, I dare you to look at the rate that you are getting. It's horrendous, especially right now with how low rates are. Okay? If you have a mortgage on a home, check it out. If you have a car payment, check it out. If you have a credit card, don't look at that one. No, I'm kidding. Check it out. Because if you notice how much higher that is compared to all the other things, that's because they're taking that money from you. The other things are what they're giving you. All right? So you want to make sure that if you're getting money, interest, you want that rate as high as possible. If you're paying interest, you want it as low as possible. Okay? The N represents the number of times that you'll be paying it in a year, and then T is the time in years typically. Okay? My dad actually taught for over 40 years mathematics at Reedley and then Clovis Community, Fresno State. He's been around a long time, since the 80s. Oh, I shouldn't even say, but when I was born, now I'm dating myself. And he saw that a lot of his students didn't understand the math that they'll probably use the most, and that's interest rates and all of that. So in one of his classes, he was presenting it, and he realized, hey, these are the educated people, and they don't even understand it. What about the rest of the population that hasn't even been to college or seen this stuff? And so he ended up writing a short little paper that he published in Fresno Bee, but it's pretty old. Okay, I put that on our Canvas if you guys had any extra free time, or you just wanted to save it when you're ready to buy a house. Okay, you want to buy a car. Two of the biggest purchases that you'll ever make. Okay, and it's important to understand because the banks have all the money, and there's a reason for that. Because they charge you guys 6 to 26%, and then they give you 0.01% in your savings and checking. That's why they make money and then can just give it to you. All right, so check that out if you want. The number E, you guys ever heard of that before? The number E? It was discovered by this fella by the name of Leonard. It's actually pronounced Euler. Okay, some people say Euler, okay, but Euler. All right, way back in the 18th century. So he came up with this number, and it actually stems from this equation and just choosing an interest rate of 1, which is why it's this. Okay, and if you see what this number goes to as n goes to infinity, it actually comes out to this value. Okay, and I'm not going to go over all that. I just want to make sure that you guys understand E is just like pi. It's an irrational number. Pi is a little bit more than 3. E is a little bit less than 3. Never end, never repeat. These are called irrational numbers. Okay? They use pi as that Greek letter. They use E. Most people think it was because of him and his last name. Others because it's exponential. Okay? So we will use this formula, which is called continuous growth or decay. Anybody that's going into the sciences, you may have heard of mitosis before. Okay, when cells split and split and split and split, so they keep doubling, for example, if they split into two. All right, so depending on the R, the rate will be whether or not it's a growth versus a decay. So this formula is just this formula with E in it. All right, so a lot of different looks that you guys will be seeing of the same thing, okay? Where this is now the money growing at a continuous rate. So the principal is the initial amount we'll put in, the rate is still the rate, time is still the time. Okay, same formula, just two different uses. All right, just remember E is a value, a number. Just like pi, it's on your calculator. All right, so here's a little how-to if you're given it. Figure out what your A is, figure out what your R is, and remember if it's positive, then it's growing. If it's negative, then it's going to decay over time because that negative exponent will end up taking that and flipping it. Okay? And then you will be able to take that, determining how long they want you to figure this out, to find the ending amount after that certain amount of time. So again, with any math problem, there are 1, 2, 3, 4. E is not a variable, even though it's a letter. Okay, it's an actual number. There are 4 different unknowns. And what are they going to have to give you? 3 of them in order to find the 4th. Okay, hopefully which 3 do they give us? P, R, and T, because then we can just plug it all in and find the ending amount. But sometimes they'll give you the ending amount, they'll give you the principal, they'll give you the rate, and they will ask you guys how long, what time will it take to make your money grow to that ending amount. Say you have an extra $1,000 under your mattress right now. Just kidding. Nobody does, right? And you want to grow it to 10,000 so that you can buy a car, the Tesla Cybertruck or whatever it is. Probably going to have to add another 0 on there, but we could figure that out based off of this. Okay? And whether it's that formula or this formula, it just depends on how it's compounding. All right? If it's semi-annually, what's a semicircle? Half a circle. So that means if it's semi-annually, that means you're going to do it twice per year, at the halfway point and then at the end. So your in would be 2. What is most interest paid in or charged in?
Monthly? Oh, yeah.
That's right. Very good. Monthly. Which means what would our in be then?
12.
That's right. Very good. What would be better? Instead of them only giving you interest every month, what would you prefer it?
Quarterly.
Quarterly is actually worse.
Oh, it is?
Quarterly means 4 times a year.
Once
Right?
a year.
I would rather them pay me, and we're talking about in your savings or whatever, instead of 12 times a year, monthly, how about daily? Give me interest every day that you have my money. Then what would N be?
65.
365. Yeah. What would be better than that?
Hourly.
Pay me every hour. What would be better than that? Minute. Seconds. Pay me every second of every second you have my money. Well, guys, guess what that's called? Continuously. And if that goes to infinity, that's where the E comes involved. Continuously. Okay? That's how you can remember it. Continuously is when you use the E. Anything else, we'll use this other formula for the number of times they want us to compound it. Okay? So just some little things in there that we'll have to deal with. Now let's get to the graphs. We kind of talked about it already. The increasing, our base, remember it's all about that base, because then there's no trouble, all right? It's greater than 1. If it's less than 1, but remember, not negative, so greater than 0, then it will be decreasing. Notice that one point that it always goes through initially is that 0 for the x, which equals 1. Okay? Talked about the domain and range and all that stuff up here as well. Horizontal asymptote, just as a reminder. Okay? Base has to be positive and not 1. These are our two options. And of course, just like we did last unit, what are we going to do with these two graphs? We're going to pick them up and move them around. We can stretch them, right? We can condense them down. All those different things that we talked about last time. And you remember, whenever we had the specific function, whether it was an x squared function, whether it was an absolute value function, whether it was a cubic, what are the other ones that we learned? Square root? Any others? Those are the big 4 that we learned, right? Remember what the shifts were for every one of these? We did the opposite for the x. And that zeroed it out. That then gave us the y value we called k. Remember that hk? That was that quote-unquote vertex for every single one of these. The only thing that changed was the parent graph based on what we were given. So guess what we're going to do with these? We're going to do the same thing. We're going to do the opposite for the x and whatever it says for the y. The only thing that will change is our base. If our base is bigger than 1, then it's increasing. If our base is less than 1, but still greater than 0, then it's going to be decreasing. That'll be the only difference. Our quote-unquote vertex, that starting place, will be that 0, 1. That's the thing that we're going to pick up and move. And we're going to shift that 0, 1 by h, comma, k. Just like we did all those others in the previous unit. Does that make sense? So if I go back to my original one that I just did with you all, f of x equals 2 to the x, and I then actually put some shifts on it, and I write 2 to the x minus 1 plus 3, who can tell me what my shift would be?
So 3 to the left and 1 down?
Richard, you said 3 to the left and 1 down. Which one is with the x?
Right. So it's the x is -1? Is that what you're saying?
It is with the x, isn't it? Up there in the exponent?
Yeah.
So that's going to be the thing that we're going to change. And remember, x's, we do the opposite.
Right. Okay. So +1.
Good. So my new vertex would shift. Now remember, it's not from 0, 0 like all the other ones were. It's from 0, 1. We would shift 1, comma, 3. So I would take, whether it's a decreasing function or an increasing function, which for this one, it would be increasing. I would take this and shift it right 1 and up 3. and then I would draw this exact same thing. However, remember that asymptote? When we say shift, we're shifting everything. Not just this point, but we're choosing that point because we know where it is. We're shifting everything right 1 and up 3, which means I would start with my asymptote. You got to watch your asymptote before you move with your exponential function, okay? So I'm going to move that right 1. Everybody ready? I'm done. Now, why am I done? Well, what does it already move? It's left and right. So if I move it left and right and it's running left and right, you're not going to see me shifting it right 1 because it runs that way. But what you are going to see is that up 3. So I'm going to take it 1, 2, 3, and I'm going to move my entire asymptote, that x-axis, up 3. Technically right 1, but you can't see that because it moves left and right. But then I'm going to take this point and I'm going to move it right 1 and up 1, 2, 3. And now I'm going to be able to build this thing the same way. Does everybody see it now? How I just took my graph and moved it right 1 and up 3 points?
So you're not only gonna move the graph 1 and 3, you're literally gonna pull the asymptote, the horizontal asymptote, with you at the base of whichever number h is.
Very good.
Okay.
Whatever k is, because it's the y value,
Constant.
right? Because it runs left and right. The only thing that's going to affect it is going to be the y value, up 3. Okay, we'll get better at these, but I just wanted to show you real quick. All right, you don't have to create a table of points. I'd rather you not do that. I want you guys to be able to do this as quickly and easily as possible, and that's where that original function, that parent function, comes into play with the h comma k that we've been using for almost 3 weeks. Okay? So we're going to take that original asymptote, we're going to move everything that h comma k. All right? So here it is. If you wanted to grab a photo of this, this is all off of the ebook. If you guys wanted to check that out, whether it's through the app or the web. Okay? And if we move our entire graph left, right, up, down, that is also obviously going to change our domain and range. What's not actually going to change, though, is the domain. How come? Well, just because I moved it up, down, left, right, notice the x's will still be all of them. Eventually, it will reach all of the x's this way, and obviously all of the x's that way. Okay? But when I move it up or down, that's definitely changing my y values. And when changing my y values, that's going to change my range. Okay? So instead of using h and k, they're using c and d in our book. I'm going to stick with h and k because that's what we're already used to from the previous unit. And I want it all to be connected for you because this is the same ideas as all the last ones. And those last few problems on the graphs, on the test that you guys did, most of you did really well. Okay, a lot of you guys saw it right away. You didn't even have to show me any work. Okay, because you knew that. All right, so again, depending on the base is going to be whether it's increasing or decreasing, but all of this stuff will just change based off of that h and k. Okay. The stretches and compressions are all going to be dependent on that a value. Okay, and the bigger the a is, the faster my y values are going to jump up. If it's negative, then we know it's going to have that reflection. It's going to change everything and flip it downwards. Okay, so that's what they mean by the absolute value. We're not looking at it whether it's positive or negative. We just want to compare it to our original one. And if it's bigger than a, it's going to stretch it to go even faster. But if it's less than 1, then it's going to be half as big or 1/3 as big. It's not going to move as fast. Okay? So the reflections will depend on whether it's positive or negative. Those translations, again, put it all together. Nothing's changed. That's the beauty of it. The only thing that's changed is now we have 2 more functions to add to our list of graphs. Okay, and these are pretty easy. Increasing through that 0.01 or decreasing through that 0.01. All right? So there's a summary for you on all these. Again, the only thing that I would change is the C and the D to an H and a K. If anybody wants to grab a photo of that, screenshot, totally up to you. Again, this is all in our e-text. I'm just trying to talk you guys through it rather than letting you read through it and fumble. Okay? So the last 2 are going to do the exact same thing. And if you guys remember, one of the last things we learned in the previous unit was the inverse. And what is inverse the fancy math term for? What English word?
Reverse.
That's right, the reverse. And if we had y equals b to the x, how would we invert that?
We would square it or square root it.
Careful. How do we do the inverse? What was our first step?
Oh, sorry, it's x equals y, and then yeah.
Yeah, we switch the x and the y. That's the simple answer, right? We switch the x and the y, we do the reverse order. But we don't like functions because we already said that this is f of x, which we could just replace with y. Can we write f of y? You guys ever seen that? Not really, right? We like the y to be by itself. So this is where we introduce these things called logarithms, or logs for short. Okay? And I'm going to teach you all kinds of different things about logs as we progress through, but I'm going to do the exact same quick run through with the previous 2 sections. Now that I explained that in a little bit more detail, I can run through these a little bit faster, hopefully. Is anybody familiar with logarithms? Have you guys seen those before?
Yeah.
A few of you? Good. Anybody in the sciences?
Yes.
You've been learning about logarithms, or have you ever seen them in there?
Yeah. Chem classes.
Chemistry for sure. That's right. So not only will you use them in the sciences, when you guys get to calculus, you'll have to use the properties of logarithms again. Okay? So make sure that you don't just understand it to do well on the homework or the test for this class. Make sure you do it to understand it for the future. Okay? The better you understand this, the easier some of those calculus as you're working through it and applying the algebra that you've learned in this class, the easier the calculus will be. All right? So what we're going to first learn how to do is take that x equals b to the y, the inverse, and we're going to learn an alternative form of that, which is, notice, log form. So we want to be able to go from exponential to log form, or log form to exponential, depending on the scenario. Right? And remember, everything has to have an inverse. Everything in math has to be able to be undone. We started with adding, and we took and created subtracting. We then took multiplying, and then just put 2 dots over that subtraction sign, called it division. Then we learned how to do repetitive multiplication, like x squared, x cubed, x to any power. And then we did the check marks. And we called those radicals or roots. Everything has to be able to be undone. Which means if we have a exponential function, guess what? It needs an inverse. And the inverse of an exponential is a logarithm. And remember, exponential is a log. And that's going to come in handy next week when I explain some of the properties of these logarithms, which are just exponents in disguise. I'll talk about that more next week. All right? Because here you can notice that we're saying y is equal to the log. Where over here, what is y? It's an exponent. That's right. That's right. So again, I'll come back to that more next week, but we need to be able to take this and rewrite it this way, or take this and rewrite it that way. All right? That is the key to doing most things concerning logs. All right? So first thing I want to make sure that you know how to do is, remember, it's all about that base. The base B will never change. It will always be this little base down here in the basement or here to the exponent. So if you ever have a log and you want to get rid of it, right, just cross it out. And notice we have b to the x equals y. But remember, we can't just cross out the log. We have to do the inverse to get rid of it. Just like adding, subtracting, multiplying, dividing, squaring, square rooting. And Ricky told us, in order to do that, we got to switch the x and the y. And notice if I do that, I'll now have b to the y equals x. Okay? So it's very easy to get rid of logarithms. You just cross it out and switch the x and the y. So the way that we do that here is we're going to say my base to what power gives me my log, that argument called the x. And that will give us the alternative form. Going the other direction is a little bit harder. Okay? But let's talk about what the options are. Well, remember, the base with all those had to be non-negative, so greater than 0, but we couldn't have a 1. Same thing then holds true for logarithms. We cannot have a negative value. All right? So that base down here, make sure that you write it down in it's called a subscript down below, can also not be negative, and we don't prefer it to be 1. Okay? Know how to rewrite it. And then if I wrote this down, you guys all would know the answer is what?
3.
Good. How did you know I wanted the square root and not the cube root? Or a 4th root? Or a 5th root?
You didn't put it on the thing.
That's right, Brianna. I didn't specify that I wanted a cube root. So this is called the common root. It is the most commonly used root or radical. It's called the square root. And therefore, we don't put the little 2 in there. It's implied that if it's not there, that is a square root. Well, then what happens if I put this? What is my base if I don't put anything? What's the most commonly used base in the entire world?
10.
That's right. You guys all would have shouted that from the rooftop if we were in any other country other than America. And you laugh, but I'm serious, because what does everyone else in the world use? What system for measuring?
Metric system.
And the metric system is all base 10. Our system, it's all over the place. You change from inches to feet, feet to yards, inches. All those things change. Even our measuring system for pounds, weight. Okay, all of them, they're all different all the time. Where the metric system, you just move over the decimal in either direction. In one of these 2-hour sessions, I could teach you the entire metric system. You wouldn't have a feel for how many kilometers it takes to get to LA, but you would at least know how to do them because it's very simple. All the conversions. Okay? So when we write a logarithm and there is no base down there, it's implied just like with the square root that there's a 2 there. That means we are base what? 10. That's right. Okay, so if I wrote log of 100 and I want to know what that's equal to, anytime you see a log, what should you be thinking? What are you looking for? What kind of thing?
Exponent.
That's right, an exponent. And so if I write the log of 100 and I want to know what that's equal to, What is my base?
10.
I'm looking for 10 to what power gives me that log of 100? So 10 to what power gives you 100?
2.
Very good. So the log of 100 is what? 2. Because if I rewrote that, you'd have 10, switch the input and the output. Remember, the base always will be the base. We're just switching the input and the output. That's a true statement. Okay, so those are some of the things that we will do within equations, and that is called the common log. Okay, there's another one that we will also use. It's called the natural log. Okay, and remember the natural number e. Naturally, can you guys hear it? Naturally, that's what you're going to use. But we're not going to write it like this. Log of some number base e, because that looks like we're looking for log x. Okay, so to let you know, so that I don't have to write that weird number e, we're going to put ln of x. That is equivalent to saying a base of e. We're just not going to have to write it. Notice I put a cursive L. Everybody look at me right now. Okay, 3 of you looked. I don't know about the rest. Do not put this. When you type a capital I, it looks like this, doesn't it? People will get these wrong all the time because they put capital I, and you can't tell if it's an L or an I. Okay, it's a logarithm. It's always going to start with an L. So to make sure that I know, I always put my cursive L. All right, just a word to the wise there. Do not put capital I. Okay, so that is what is called a natural log, and that is so that we don't have to write that base of e. It's implied. So if you see ln of x, naturally you're going to be thinking of e. Okay. All right. So those are our logarithms. Let's talk about how to graph them, and then we'll get into our breakout groups so that you guys can start practicing some of this stuff. All right. So our logarithms are either going to look like this or like this with the base of e. And by the way, is this an increasing function or a decreasing function?
Increasing.
How do you know that, Richard?
Now that I think about it, I don't, because I don't know what the variable is.
You don't need to know the variable. What did Megan Trainor tell us?
There's not a leading negative coefficient.
Doesn't matter. It's all about that base. You're right. It does matter about that negative coefficient. You are correct about that. But remember, to tell if it's increasing or decreasing, what is E?
2 points.
You need the E. You have to borrow. That means it's a little bit less than 3. Okay. Pi doesn't have the E, so it's a little bit more than 3. I don't know if that helps you to remember. Okay. But very good. You're absolutely right, Richard. The ln of x has a base of e, which means it's bigger than 1. It's going to be increasing. But remember, when we graphed, let me go all the way back up top to these exponential functions. Exponential functions have a horizontal asymptote along the x-axis. What do we say logarithms are to exponentials? The what, Ricky?
Inverse.
The inverse, which means if exponentials had this as an asymptote, what are logarithms going to have?
They're gonna have these horizontal.
No, the exponential already has this. What does that mean ours is going to have? If it's
Vertical.
y equals 0, it's going to become what?
Vertical.
Yeah, it's going to become x equals 0. Remember, logs come from trees, straight up and down. Exponential functions run along the x-axis. And because these both share the point 0, 1, what is the inverse of 0, 1?
1, 0.
Very good. So logarithms will have this as the asymptote, x equals 0, and instead of 0, 1, it will have the point 1, 0. And how do we tell if it's increasing or decreasing?
The base.
It's all about that base. That base, you guys, then there's no trouble. If it's increasing, then I will start down here and do this. Can you guys see my beautiful butterfly that we talked about last unit? The increasing one here versus the increasing one here. And what about decreasing? It'll start up there and go through that point 1, 0. That one's a little harder to see because I've cluttered it. Okay? But that's exactly what we're going to be doing with the graphs of these logarithms. Let me get back there. Can you see it? Instead of the x increasing, we will have logarithm y and that point 1, 0 and increasing because of my base. It's that simple. Guess what we're going to do to these now? That orange one. And guess what we're going to shift by, everyone?
H and K?
You got it. Opposite for the x, same for the y. So this and this, my parent graph, I will just shift by that 1, 0 now instead of 0, 1. And the asymptote, which I do it in reverse order. Take care of your asymptote first, right? By H, K. And I'll write that down for you all. I'm going to call it the vertex. Just so you know, I mean the starting point. That's it. That's the big change from last unit to this unit, is we're simply adding 4 more functions. And in reality, 2. Exponential, but increasing, decreasing. Remember, exponential along the x-axis. And logarithms, logs come from trees straight up and down the y-axis with increasing and decreasing. Instead of going through the point 0, 1 for increasing, decreasing, now we're going to go through the point 1, 0. Increase, decrease. You guys got that? So again, that is going to change our domain and range. In reality, it's going to flip-flop them. Now we will have all the y values for these things. Everything up here, everything down there. Everything down here, eventually everything up here. So our domain is now going to be restricted from 0 to infinity. From 0 to infinity. And if we shift, then that's going to change things. Okay, but remember, it's all about that base on telling whether or not it's an increasing from left to right or it's decreasing from left to right. And our measuring stick is a stick. It's the 1. Bigger than 1, increase. Less than 1, but still positive, decrease. Remember we said it can't be 1. Okay? So our translations, again, H and K. Don't worry about the C and the D. There's a summary. Here's an example, and then we're done. Can you guys all graph that quickly? Go for it. So help me out. I know I didn't give you a ton of time, but I want to give you guys more time to work together in the group quiz. Is it increasing or decreasing, first of all?
Increasing.
How come?
The base is 2.
Good. Richard's got it down now. We are increasing because of our base of 2. What is my vertex?
-2, -5.
Very good. -2, -5. Because remember, we always take the opposite for the x. Y's are y's. We keep it. Now, what am I going to shift left 2 and down 5?
The asymptote.
Very good. Technically, the answer is everything. But we're going to start with that asymptote. That's right. So I'm going to take and I'm going to shift everything. Now, where does my original asymptote start?
X-axis.
Careful. Exponentials will be along the x-axis. Remember, logs come from trees. It's going to be straight up and down on my y-axis. Does that make sense?
Yes.
Exponentials along the x-axis to start. Logarithms from trees straight up and down the y-axis. So I know that this is going to originally be here. And if you guys want to, very lightly, we can take that. Hopefully you can even see that yellow. I'm trying to do it very lightly. And I'm going to shift that, like Marcos told me, left 2 and down 5. Now, when I go left 2 and then down 1, 2, 3, 4, 5, doesn't it run up and down? So notice the down 5 didn't really play anything into it, did it? But the left 2, I definitely can see. And by the way, Marcos, that's a beautiful picture of yourself. Okay?
You guys can see that?
Yeah, I thought you knew.
No,
So
I'm using my sister's computer, so that's why.
gotcha. No worries. So left 2, you're not going to really see the down 5. So I'm going to do that one now in a different color. Let's do it in red. Left 2, down 5. Now, what else should we be shifting? And by the way, let's finish. What is the asymptotes equation? Are all the x's the same value or all the y's?
All the y's.
All the y's are, so this y and this y and this y, they're all the same?
The x's are the
I
same.
mean,
Ah, good. Do you see that? It runs up and down. So all the y's aren't going to be the same number. They're all going to be left what?
-2.
So very good. My x's, every single one of them, here, 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 and here, are all left 2. My y's, you can see, are everything. So that's the asymptote. And then what are my points that I'm going to plot? Well, what is the original one that we said it would be? 1, 0, right? We're going to take that and we're going to shift it, like Marco said, left 1, 2, and then down 1, 2, 3, 4, 5. And from there, Richard helped us out and said, Because of the base, it's going to be increasing. So from this point, I'm going to go left 1, 2, 1, 2, 3, 4, 5 down. And then I'm going to draw it as an increasing function. And if I wanted to find exactly where it crossed through the y-axis, or eventually where it crossed through the x-axis, do you remember what we called those?
Intercepts.
Very good. The x and y intercepts. Do you remember how to find those if they ever asked?
Set them to
Y equal to 0.
Good. Which one would be y equal to 0 and which one would be x equals 0? Well, if you're trying to find the x, that means you're going to let y be 0, and then you're going to solve for the x. If you're trying to find the y, then you want to know the y, so you're going to let x be 0. Does that make sense? And we'll get there on how to actually do that. What happens when I let this be 0, or what happens when I let this be 0, one at a time, by the way. How would I solve that equation? We'll get there. We're not quite there yet. Okay? So my friends, this is it. That is the graph. So who can tell me what the domain is? How do we read?
Left to right.
For the domain, that is the x value. So I definitely want to go left to right. Am I hitting any values on my graph yet?
No.
Not until I get to what number?
-2.
And will I ever touch -2?
No.
No. So what number should I start with here?
-2.
Yeah, I actually want to start at -2, but make sure to not what?
Include it.
Include it. So I'm going to put a parenthesis. Because -2 is not an x value that I can actually put in. Okay? Then what? What are those x values going to hit from there?
Infinity.
Positive infinity.
Yeah, very good. Do we ever include infinities?
No.
Then open parenthesis around those. How about my range? Those are my what values?
your y.
My y values, very good, Richard. And just like this, we went smallest to biggest from left to right. Now I want to do smallest to biggest, which means I'm going to start at the bottom and work my way up. That's what all of you guys are doing, right? That's why you're taking this class. You're going to work your way up. So what am I hitting anything down here on my graph?
No.
Actually, yes, Richard, because what does this mean?
Infinity.
Yeah, it goes down forever. So you can't say just because I ended my arrow here, oh, I'm at -8. No. This arrow means it goes down what? Forever.
Infinity.
That's right. So we're actually going to start, I know that's weird, at -infinity. And it's going to go eventually, it's slowly, but it does keep going up. Right? There is no horizontal asymptote on this. It's going to slowly and continually go up to what?
Positive infinity.
Which again, we would never include either of those. And that's anything and everything that they could ask us about a graph. The only thing that they could throw on here to make it a little bit more challenging is a negative, which would then flip it. And it would, instead of being a increasing graph, it would become a what?
Decreasing.
That's right. That's all I got for you guys. Hopefully that was enough. All right. If you guys wanted to do another one, you could, but I think you guys get it. All right. Just remember that this here is a what kind of graph?
Exponential.
Increasing.
How do you know it's an exponential and that it's increasing? Very good, you two. How do you know it's not a logarithm?
Doesn't say log.
It doesn't say log. Beautiful. And because it's a x up in the exponent, we know that we're going to start along the x-axis with that 0.01. And increasing, we're going to take that and shift it what?
Right 1, up 3.
Beautiful. What are we going to shift right 1 up 3?
The asymptote.
Everything. Very good. And we're going to start with the asymptote and then take that 0.01 and then we'll just redraw this. Beautiful. Excellent job, guys. All right. Any other questions before I stop sharing screen? All right.